So you could probably do this in any order you want. I like finding this one, and there's lots of different ways to find these. There's alternate interior angles. There's same side interiors here. There's triangle sum theorem. There's so many different relationships now because we have parallel lines, and we also have triangle relationships. Gives you lots of overlapping ideas. My vote for the easiest one on here to find would be y. If you look at that little z shape, y should have been 50. You could directly get that from an alternate interior angle. X should have been 40 because that right triangle corollary, this triangle angles add up to 180, get rid of the 90, and those have to add up to 90. These have to be complementary. Z, you could probably get it from the 50, but most likely if you found this was 50 down here, you'd probably say, well, 50 plus 70 is 120. That leaves me 60 for the top angle. Probably we use the triangle sum theorem. Wouldn't have to, but probably would. There's other ways to arrive at that, certainly. So holy cow, I've really done you a service here by giving you a quadratic, another quadratic. Hopefully you can see all those clearly. I'd pause it again for now. There's little congruent marks here that are incredibly important there. That helps you. 74 degree angles up top. So you can find X and Z in the last one. And this one takes a few minutes. So this is a classic example of a third angle's corollary. There's overlapping triangles. That's why I have the yellow color up here to see the overlapping triangles. And they have two congruent angles. This triangle has a 74 and a whatever that is. And the white one here has a 74 and whatever that is. Which means these have to be equal to each other. I would argue you can't find Z until you find X. So if you set those equal, a little subtraction on here, you should realize there's two potential values for X. Classic GCF problem, factor out the X, and you get two answers. -9 is a possibility, and the other one, 0. Now, if I plug the 0 back in, this wouldn't exist. That wouldn't exist, so I'll get rid of that one. But the -9 works. -9 squared is 81. 81 minus X is 72. So it is certainly possible that those angles, could both be 72. And that one would be the same thing, 72. Here's where the progressive steps here come in. These are 72 and 74. That's what, 146. Hopefully I did that right. Which would leave a certain amount for this angle. That's got to be 34 for my congruent angles. Those right there. And there's two of those. 34 and 34, 68 degrees. Now I'm looking at where Z is. Z is vertical to the one that's missing here. So if you know those are 68, a little subtraction from 180, you can find this vertical angle from Z, and you should get 112, as you may have seen it came up a minute ago. That's a lot of steps. Solve for one angle. These two angles lie to get the third angle. Third angles lie to get fourth angle, and the fourth angle is vertical to the last angle. Gotta love that. Hopefully that made sense. All right, last one. First thing, two congruent angles on there. That's helpful. Second thing, the exterior angle that you have to create by extending the side. I like making you draw this so you can see, boop, I just created linear pairs and there's a relationship on there. It's called an exterior angle. That's it. That's all you need. And I want you to evaluate the scale in the drawing. You know, a lot of you like to criticize Mr. Hess's drawing. Jacob Lehman will be raising his hand. James will be raising his hand. Drawing's not to scale, Mr. Hess. Yeah, I know. I just sketched it. It was just a quick sketch. Give me a break. Cut me some slack on here. Talk about the scale of the drawing. This is the time to criticize. Mr. Hess can't draw. He's a knucklehead. He can't. This is the time. This is the opportunity to talk about the scale of the drawing based on the value of X. Go for it. So if this was 5x plus 24, of course, that's the same thing. So those have to add up. And then those two angles add up to, I don't know about this, but they do add up and equal whatever the heck that angle is. There's your relationship you're expected to find on here, your quadratic relationship on here, your remote exterior angle relationship. A ton of different ways you could solve this. You certainly can combine like terms. You could move these over right now. Somebody in the room probably realized that that's divisible by 2, 2, and 2. You could reduce that. The order doesn't really matter a whole lot. Hopefully at some point you realize you can reduce that to x squared. Half of 10 is 5. Half of 48 is 24. And it is factorable. Another quadratic situation on here. I'm thinking 6 and 4, no. 12 and 2, no. 24 and 1, no. 8 and 3, hopefully you came up with those two. And the 8 must be negative here. 0 product property, tell me that's 8. That one's negative 3. And this is where you can criticize Mr. Hess and say, well, like, if this was 8, Mr. Hess is crazy. Or if it's negative 3, Mr. Hess is crazy. Only one of them makes sense in the scale of the drawing. I would argue the 8 makes more sense in the drawing because this angle appears to be obtuse on your paper. And if you plug the 8 in, you get 128 from this angle. The negative 3 would give you a much smaller angle. It's possible that the drawing's not to scale and even it's negative 3. But most realistically, this part's acute and that part's obtuse with the scale of the drawing. And the same thing up here. These would both be 64. And they both appear to be acute on your paper. Hopefully that makes sense. Try that homework assignment out. It goes with this very nicely. It pairs a couple quadratics. I think there might be a system in there. You're going to love it.